All right, so welcome to this colloquium. It's really a very special honor for me to introduce Inga Kamp today. So Inga Kamp is one of my longest collaboration partner. She's on a European tour, and we get an audience today. So Inga started her career in Kiel in Germany by doing a PhD on stellar physics, actually, so abundance analysis. Many of us started in stellar physics in these years. Then she went to Leiden by a Marie Curie fellowship. And there she developed the CoStar program. So she switched topic and was interested in CO observations of debris disks. And so she developed a program, a theoretical program to understand this phenomenon. And this was Prodimo reaggregation 0. So that was the work that Prodimo is based on. And then in 2004, she went to the Space Telescope Institute in Baltimore in the US, working for ESA on science archiving things. Tough time, 2007. And then 2008, she was successful with an application to Groningen University, where she still is. And so she became a full professor there since, I don't know, 5 years or so. Yeah. So Inga was involved in a lot of large consortia that observe protoplanetary disks. So in particular, she was involved in Herschel JWST, where we wanted to detect fine structure lines in disks. And there, actually, Prodimo was developed in close collaboration between us. And then she also is now, since 2008, we just talked about this. So in 2008, she became involved in the JWST. She's a European co-PI of the MIRI instrument. And only now, so after 15 years of work on that, she is now heading this MINDS team. It's one of the four.
Thomas Henning is a PI.
Okay, yeah.
I'm the co-I.
But she now has really a lot of publications dealing with these new results. And this is also the topic of today. I just want to say, so Inga is actually the colleague with which I have the most common papers. So 92 of 199 papers are together with Inga. And for you, it's similar.
Yeah.
On half of my papers, Inga is so today she will talk us about a new window into planet formation with JWST.
Okay. See. So this should be on now. Perfect. Well, first of all, thanks a lot for the invitation to come to Graz. It's my first visit here, so I hope I will really enjoy the time. At least I'm looking forward to talking to many of you. And today I would like to just showcase a couple of things that came out very recently, and it's most work that we did with data from the James Webb Space Telescope, mostly with the MIRI instrument. So I'm a co-I of the MIRI instrument, and that's why most of the guaranteed time we spend on the MIRI data. But I would also like to show a few results from one of my PhD students in Groningen. It worked before. This is the way how it works. So just to give you an outline of the talk, I would like to start with a very general introduction into planet formation and disks, just to give you the mindset with which we are carrying out this work. And then, as I said, I would like to talk a little bit about the work of one of my PhD students, which is more focusing on the dynamics, so trying to capture what happens in the very, very first stages where we start to form planets, more pebble formation, planetesimal formation. And then most of the time I would spend on showing you the latest results of JWST data for disks. And there I would like to focus mostly on taking the next step, because so far we've been doing a lot of inventories about which molecules we see. But I would really like to take the next step and confront these models confront this data with more detailed models. So first, a short introduction. So where do we actually stand? I think this is a famous iconic image of HL tau. Everybody knows it. This was when the longest baselines of ALMA became available, and we realized these disks are not as smooth and simple as we thought. So many of these disks actually show a lot of substructure. And very interestingly, so this was a fairly young object, less than 1 million years old. And subsequently, people, of course, used the same long baselines of ALMA to look at a huge sample of disks. This is just a small subset from recent review articles, also by Bay et al. From PP7. A lot of these disks simply show substructure. And so even though we do not want to make the direct link and say like each of these little rings or each of these little gaps means that there's a planet inside, we do think that these disks are shaped and substructured because of the processes that form the planets. And so more interestingly, recently, there was an even younger disk. So this is by Sibura Cox, 2020, a disk which is less than 500,000 years old, also already showing substructure. So this is telling us a coherent story, namely that probably the very first processes that lead to planet formation, the very first steps we need to take, they occur very early on. And this is very consistent with what we also find when we measure, for example, disk masses. And we find that disks, when they are in this evolutionary stage, so when they are like a few million years old, they typically do not contain enough material to make the planetary systems that we observe nowadays. While if we measure disk masses in this phase, we have enough material to make planets. And so maybe, you know, all of this hints to the point that planet formation really starts early. Now, ALMA is one of our windows into understanding planet formation. It gives us mostly observations of the outer disk. So you see here for comparison, our own solar system. And so with ALMA, we can typically resolve the disks down to maybe a few astronomical units in the continuum. If we look for the gas, it's a little bit worse because gas lines require very deep observations and we do not get, say, as high quality images. So often we do not go for the highest resolution. So most of the ALMA data actually gives us information, I would say, for beyond 5, 10 astronomical units. So we get the outer part of a planetary system. And in that sense, JWST, we were looking forward to it so much because it's very complementary, because it works in the mid-infrared. It's not only, so I don't want to make the point that we are spatially resolving these scales with James Webb, because after all, it's only a 6.5 meter telescope. But because it traces the mid-infrared emission, the mid-infrared is where we have low vibrational emission of molecules. And to excite low vibrational lines, we need high temperatures. And those high temperatures, and here I'm talking about a few hundred to maybe a few thousand K, those are the temperatures we find here in the inner disk. So with the outer disk, we see also molecules, but it's cold molecules, maybe a few 10 Kelvin, maybe 100 Kelvin. With MIRI, we see the warm gas. And that pertains to the terrestrial planet forming region. So we are clearly seeing emission from inside a few astronomical units. And this is very interesting. And we used it to design a survey that contains a large number of these disks. And now you could say, well, these class 2 disks, maybe it's not that interesting because planet formation starts early. But just to remind you, and I know Helmut is in the room here, even Earth accumulated a significant chunk of its material very late. So even if we observe objects at an age of a few million years, they are probably still in the phase of assembling here in the inner part their terrestrial planets. And so that is the relevance also of MIRI for getting this planet formation picture complete. Now, I know there are different pathways how to make planets. Gravitational instability supposedly works very quickly. Many people would say core accretion is a more favored scenario, and then you have people who want to do it via planetesimals, or people who want to have pebble accretion. So there are all kinds of different ways how to make planets. Maybe we form these larger particles, so you can call them pebbles if they decouple from the gas, and then if you through, for example, streaming instability, you could make from these pebbles planetesimals. And then it's a competition between planetesimal and pebble accretion that is eventually making the planets. But there are 2 points I would like to make here, which I think are very important. The first one is that all these dynamical processes that people invoke to make planets, they depend on what the disk structure is. Because the way how the pebbles move in these disks, how they drift inwards, how fast they drift inwards, but even how fast they grow or how fast they settle to the midplane, is entirely determined by how we distribute the mass in the disk and what the temperature of these disks is. And so it is absolutely essential that we use all these beautiful ARMA observations of the outer disk to tell us what is the context, what is the background on which these dynamical processes happen. And the second point I would like to make is that there is a lot of evidence from the solar system that planetesimals in the inner disk also likely formed very early. So these kind of things, for example, if you want to invoke the streaming instability to make planetesimals, very likely this also happened very early on. And that led us to asking the question whether the volatile composition of planetesimals is actually affected by these disk processes that happen, all the transport processes. And so that brings me to the first point I would like to make, that is introduce you to a new study that tries to link in a very comprehensive way the dynamics that happen in very young disks that are younger than 1 million years, together with the chemistry. And so what we do is of course, we do not forget about the disk models, because that's, what I started out with, and same as Peter, these are our favorite models. So we do not forget that we have Podimo, which gives us the density distribution, the chemical distribution in these disks. And we use that to calculate this for a very young disk. So we do time-dependent chemistry. We start with molecular cloud conditions. We generate our chemical and physical structure of a disk around a star, which is about 500,000 years old. And then we use those conditions. As I said, it will be the surface density, it will be the temperature at any point in the disk that determines how the dust grains are growing and how they are moving through the disk. And so the idea we have is these dust grains are composed of tiny little monomers, as we call them. So a big dust grain, a pebble, if it's a centimeter in size, can be composed of like 10 to the 9 of these small, tiny monomers, as we call them. They are the constituents. The point is that at any moment in time, you have growth processes in the disk that build up from monomers, large dust grains, but you can also have collisions that liberate the monomers again. And all of this affects how your particle is drifting through the disk, because you drift differently. If you're very small, you follow the gas. If you're very large, you can do your own thing. And it's only the gradients of the gas that affect how you're drifting. And this is what we really wanted to follow. And we couple that with the chemistry. So we have this monomer concept. We can let loose a monomer anywhere we want. In this particular case, we let it loose at 10 astronomical units in the midplane. And we just followed what is its collisional history, because it will grow in time. Every now and then it makes a catastrophic collision, it breaks up. It grows again, or it's kicked out in a collision. So we have all these processes, coagulation, fragmentation, erosion, that follow the particle. And if a monomer is very close to the surface of this big particle, it can actually accumulate ice. Yeah, and so depending where the monomer is in the disk, it can either accumulate ice from the background model, or it can lose ice because it's simply in a warm region. And you see here how that kind of walking around of the monomer happens. It's a stochastic model. So depending on what fragmentation speed you assume, so the fragmentation speed is when we have two dust grains colliding, we assume in the blue case with 1 meter per second collision that they fragment. The other cases, the dust grains are more stable, they fragment only at higher velocities. But if we focus on the blue one, you see that the temperature that our monomer experiences as it moves through the disk is changing, because it's moving first a little bit inward, then it's moving outward again. Every now and then it makes excursions to the surface. So we capture all of that. And now the question is, what does it mean for the ice composition of this monomer? So instead of having one monomer now, we use thousands of monomers because we can let them loose everywhere in the disk and try to sample in a statistical way how the final products look like after 100,000 years of evolution. And what this figure shows you is what is the mass fraction of ices that we have. And the color coding now tells you where is the material coming from. So you see here, as a function of distance, we can look at any point in the midplane and check whether at this point, the aggregate we are looking at has a composition that is coming from the outer disk, or is it coming from the inner disk? So the color code tells you anything that is beyond the water snow line is coded blue. Anything beyond, anything beyond the ammonia snow line is blue. Beyond the water snow line is orange, and then you have the other snow lines. But for example, if we look here at 2 astronomical units, you see that only 60% of the material actually diffused outwards from inside the snow lines, ice lines. All the other material came from either beyond the ammonia or beyond the water snow line. So we find that especially in the inner disk, because these ice lines follow each other very close in space, the inner disk shows actually quite a diversity of where we get our material from. So the composition will be very diverse in the inner disk. If you look at the outer disk, it's very homogeneous, simply because there are not many closely spaced ice lines. You are beyond the snow line of CO or not. No? And so in that sense, if you look at monomers or dust aggregates inside a few AU, they originate from a chemically more diverse environment than in the outer disk. And the second effect we found is when we compare our results, and that is a solid line here from the shampoo code, with the results from a steady, from the background disk model, which is a Podimo model, where we follow the chemistry and everything as a function of time, we see that especially around the location of the ice lines, the water ice line is the blue line here, the CO2 ice line is the green one, especially around these ice lines, we have a huge deviation between the 2 codes. For the rest, I think we are very happy. We show basically that the treatment we have in our code is not so bad. It's giving us the same answers, whether we use shampoo or Podimo. But especially around the ice lines, we found a very interesting effect, and that is because if you look at a monomer, it is statistically mostly buried very deep in an aggregate. If you're buried so deep, you cannot take up ice because you are basically surrounded by 10 to the 9 other monomers that block you from seeing even the surrounding nebula, the surrounding gas. And so what we see is that as we approach the ice line, we can already start to desorb ices because it's getting warmer and warmer, but we cannot take them up. And this is a fundamental difference between Podimo and the shampoo code, which does the dynamics as well. So there's this kind of collisional mixing going on, which makes the monomers very often part of the deeper aggregate. And so they cannot interact with the gas and ice in the disk. So I think these were 2 important lessons, and we are still trying to digest what this means in the long run for planetesimal formation. But let me focus now for the rest of the talk on observing the chemistry in the terrestrial planet-forming dome. And obviously, JWST is not the first instrument to observe the inner disk. We know we stand on the shoulders of giants. So there was a Spitzer Space Telescope. There were a lot of people who worked on this, like Colette Salik, Klaus Pontoppidan, Ilaria Pascucci, all of these people, Jonah Jeter. They noticed already that there are many, many molecules that reside in the inner disk, like water, OH, CO, CO2, HCN, acetylene. They had all been seen with Spitzer. And of course, we knew we had a limited amount of guaranteed time. So obviously, we picked all those disks where we know we find these molecules. But we knew JWST would go a factor of 50 deeper in sensitivity. And we have a factor of 5 higher spectral resolution. So we can really deblend some of the features that we see here that are all kind of smushed together. With JWST, we will actually resolve them spectrally And in many cases, we have very prominent Q branches, like here for HCN, for example, C2H2Q branch. Those were sometimes unresolved spectrally with Spitzer, and that limits your interpretation. Now we can spectrally resolve them. And one of the very important things, and I will come back to that, that Spitzer already noted is when we look at very cold stars, much cooler than the sun, and we look at sun-like stars, they show a dichotomy in composition. So the sun-like stars show proportionally, so compared to acetylene, much more HCN. And already at that time, Ilaria Pascucci noted that, and it was something we desperately wanted to follow up on. So in our sample, we do have actually both these type of objects. And just to make the point again, of course, MIRI covers the inner disk or Spitzer in the past, but now we can link it with the ALMA observation. So we have the same kind of chemical species that we trace in the inner and outer disk. This is just to give you an overview of the MINDS program. We have about 50 objects in total. 10 of them are what we call brown dwarf disks or disks around very low mass stars. Most of them are sun-like stars, so T-Tauri stars. We have a couple of Herbig disks. The problem with the Herbigs is they're too bright, so they saturate the instrument. There are very few we can follow up on unless you want to throw away 75% of your data and focus on the longest wavelength channel, but all the other data is useless. We also have TW Hydra with a coronagraph, and just last week we got the data, so now we can look at it. Our program in total is about 95% complete. We are just missing 2 objects, so that's really super cool. Now, if I were to give you an overview of what we already had, I mean, this would be a very, very long talk. So just to give you the idea, we have seen lots and lots of different things. For example, the isotopologue. So Spitzer saw the main isotopologue of a molecule like CO2. Now we see the rare one, 13CO2 as well. And as Eileen also always likes to put it, most of the information is in the weak features, in the weak lines, because the strong lines are often optically thick, they saturate. And so if you do modeling, it is really the weak features that help you a lot. We saw in the disks around very low mass stars a molecular quasi-continuum, and I will come back to that. We confirmed something that I would say from the thermochemical models, we always told people this is the case. So there is a gradient in the excitation of water as we go from the low vibrational band at 7 micron all the way to the rotational lines at 25 micron. So we clearly see temperature gradients in the disk surface, and the water lines originate slowly, increasingly outwards as you go to longer wavelengths. So lots and lots of results. But let me just focus on a few key points. The very first thing we wanted to get across is, if we look at these disks, there are no 2 disks that look the same, which I think is a very important message to get out. Even though I said earlier that sun-like stars and very low mass stars, I mean, they fall into 2 groups. That's true. But even if you look at what we have in terms of sun-like stars, they all look different. This is just a model, which is a very simple 0-dimensional slab model, just the column density at a certain temperature to guide the eye. So this feature here that you see at 13.6 is acetylene. And interestingly, we see the isotopologue of acetylene now as well, 13C, 12CH2. The little blips here in blue are water, and actually this kind of color here, this is HCN. And so also when you look at these very low mass disks, or disks around very low mass stars, you see they all look different. If you just compare, for example, the location here, HCN, how strong the HCN region is compared to acetylene, it is very different among those 3 objects. So very early on, we noted every object is unique. Every object you can write 3 papers on easily. So we are really very rich in data, and we are very, very happy about all the stuff we can get out here. Now, let me go one step further and present you one individual object. It's one that I worked on together with Matthias Samland, a postdoc in Heidelberg, and also Thomas Henning when I was visiting there for a few months. And there are a couple of very interesting, stunning things. Hydra is a disk that we see face on, almost face on. And if we zoom in, this is the ALMA image, we see that the inner disk on a scale of an astronomical unit has substructure. There's a tiny little inner disk, and then there's probably a little bit of a gap, and then an outer disk. And when we analyzed this disk, we saw that the spectrum was totally boring shortward of 14 micron. There was no water emission whatsoever, which tells us immediately, we can do very simple estimates, that that inner disk does not contain any water, at least not significant amounts. And then here in that wavelength region at 14 micron, we started to see the first water lines popping up. But interestingly, on the contrary, we saw very interesting molecules, namely molecular ions for the first time. HCO plus, this Q branch here, had been seen with Spitzer, but it was just like one little blip, and people said like, well, could be HCO plus. Now we see more than that, because usually a Q branch is accompanied with a P and R branch lines as well, to the right and left. And we do see some of those features as well, even though we have to say we are really getting close to the noise level here. And another very important molecular ion we found is CH3 plus. This had been seen earlier in the PDRs for All program. Olivier Bernet has published a paper about that. In that case, it was a disk that is externally irradiated with a very, very high UV field because it's in a very massive star-forming cluster. And here we see that molecular ion in Hydra. And this is super, super interesting because it led me to actually look back at our thermochemical models. Now, how can we understand these molecular ions? What I show here is, in green, a slab model. As I said, it's just a column density of the HCO plus molecule at a certain temperature, and then I can overplot it, scale it with the emitting area of the molecule. But that is just the first step to see, what molecules do I have? But really what we want to do is to model it with physics and chemistry included, and really provide context and understanding to why do we see these molecular ions, for example, only in Hydra and not in the other disks. And this is something we can only do when we take our thermochemical models and use them as little laboratories to investigate a bit what the options are. This is again a sketch of Hydra with this tiny little inner disk. And then we have a rim here. And the rim, we know from interferometry, is about 2.4 AU at that position. And if we make that rim a gradual increase in column density, what we get is actually a region which is spatially a little bit extended, but it has very much PDR-like properties. It's very irradiated from the central star, and it allows molecular ions to live in that region where you have strong UV radiation, still high densities, before you enter into the completely opaque part of the disk, and then everything becomes neutral. So we need this kind of zone, which is a little bit spatially extended. And we managed to get that when we say we have a kind of very gradual rim that is building up. And as you see, if we go at 2.4 AU, the temperatures are kind of right. So we are between 200 and maybe 2000 Kelvin in that region. And this is exactly what we find for the molecular ions. They have temperatures of 200, maybe 300, 400 K. So that's exactly the right conditions to excite them. Now, I told you that we do not see any water lines shortward of 14 micron. If we use our normal model with the normal abundances of carbon and oxygen, inside 2.4 AU, we find very high abundances of water. This gives you the abundance scale in color, and 10 to minus 4 is basically putting all oxygen into water. So this is the height of the disk versus the distance. And if we look at this model and we create a spectrum, we will see booming water lines all over the place. And I show that here. So that is this blue model, call it the adapted Diana model. Diana was a European project that Peter led a few years ago, and we generated all these kind of beautiful models based on observations we had. And I tweaked that model a little bit, but you see that even at 7 micron, the low vibrational bands of water would show up, while the observation here in black doesn't show them. These are H2 lines that you see here, but not water lines. And so we have to do something to get rid of the water in the inner disk. And there are two options. You can remove the gas entirely, or you can deplete the elements. And so we tried both. We take a factor of 50 less carbon and oxygen, because we also have to suppress the acetylene, which is very strong here. And if we do that, we get the orange model. We still overpredict the acetylene, but we get rid of all the water here. The second option, to remove the gas entirely, has a problem because it's a physical chemical model. So the dust grains that we have in the inner disk, they're supported by the gas pressure. If we take away the gas, the silicate grains all fall down to the midplane, and we make the silicate feature very weak. So for us, that was not a viable option. But I'm not saying that it's impossible to find another solution with maybe different dust grain sizes or whatnot. So it's still something to explore. But at the moment, with the current model, I would say we would favor that there is still gas in the inner disk, but it is actually depleted in elements. Now, another interesting target is PDS-70. And that one has been modeled originally, again, with very simple tools. So just using slab models, a column density of water at a certain temperature with a certain emitting area. And you see here only the low vibrational water band around 7 micron. The black is the MIRI spectrum, and blue is the fit that we got. The water has temperatures of about 600 Kelvin, and it comes from inside 0.1 astronomical units. Now, this is a super exciting source because we know it has an inner disk that we have seen with ALMA, and then it has a huge gap. And inside that gap, we have two massive protoplanets, more massive than Jupiter. And then we have the outer disk. And my PhD student, Byron Portilla-Revelo, had already done a very nice radiative transfer model of this source, because we compared to ALMA data to find out, like, is this gap that we have between the inner and outer disk, is it gas-free? And the answer is no, it's not gas-free. But we took that very same model and we said, what if we just predict from that radiation transfer model the MIRI spectrum? And that's what you see here. So this, actually the first version was with canonical elemental abundances, but it was already within a factor 2. And that gave us a lot of confidence to explore, again, the carbon to oxygen ratio in the inner disk to find out whether we could constrain it, not only based on this water low vibrational lines, but we took as additional constraints a non-detection of HCN and acetylene in the outer disk and the detection of CO2. And then we came to the conclusion that the carbon to oxygen ratio is slightly enhanced with respect to solar, so maybe between 0.7 and 0.9, but it's not above 1. And in the outer disk, there was a recent paper by Alex Kriegland that said, from ALMA observations, they would infer a carbon to oxygen larger than 1 for the outer disk. But I'm bringing up this as an example to show you how we can now combine ALMA observations and MIRI observations to say something about elemental abundances across the entire disk and to test all the hypotheses that people have about how you may or may not transport icy pebbles in these disks. It's very clear that just the sheer fact that we see the water in that tiny inner disk here means that it needs to be replenished constantly. So we know there is material flowing through the gap, whether it is water vapor, water ice, or whether it's hydrated minerals, we don't know, but something is replenishing the oxygen in the inner disk. And one of the interesting things about this very, very hydrocarbon-rich source is that we work together with another PhD student, Inga Kamp, who also was here in Graz and will come again, to expand our understanding of the hydrocarbon chemistry. And what you see here is a disk model, like how would a thermo-chemical model look like if we modeled such a disk around a very low mass star. And this is with the ordinary carbon to oxygen ratio. And all this in color, these are the molecules that we have seen in the JWST spectrum. All of them exist in our models in this inner region, but they exist typically below the optical depth 1 surface. So they sit very, very deep in the disk. Now, if we change the carbon to oxygen ratio, as we would also think from the spectrum, make it larger than 1, all of these molecules start to show up in the surface above the tau 1 RD. So I think we can conclude, even though we do not know what changes this carbon to oxygen ratio, these sources clearly have a high carbon to oxygen ratio, and with gas phase chemistry, we can at least understand the existence of all these hydrocarbons. So I think that's a very important message to take away. Now, of course, there's much more. We would like to understand the physical processes. We want to understand what happens in these disks, how they evolve, how certain parameters change the appearance in the spectrum. And a lot of work, because JWST was delayed so much, a lot of work happened in the absence of data, which is maybe good. Now we can confront it. So there have been several studies, for example, who looked at how does carbon to oxygen affect the mid-infrared spectra, how photochemistry affects the spectra, but also how disk structure affects these spectra. And one of the things we did is from the Diana project, we had about a dozen models that we had done thermo-chemical models based on a huge range of observations. So we had a good idea from the SED fitting, from line observations, what kind of disk structure we would find. And this is only a schematic of the disk structure. This shows you the scale height of the models as a function of radius, and in color, the dust to gas ratio, or gas to dust mass ratio. And it also shows you where there's maybe a gap in the disk. And the only case I want to make this just showing 2 of them here. But these 2, if I calculate the mid-infrared spectra and predict what MIRI should see, they look very different. And so one of the lessons learned is that maybe if I have inner disk structure and I carve out a region where a particular molecule sits or where it likes to be excited, I can remove that molecule from the spectrum simply because further out it's too cold. I will not excite it anymore. And so I think it's a very interesting thing to follow up on to see how does inner disk structure affect the appearance in the mid-infrared. Another thing we tested is if the dust grains evolve, so if they migrate inwards, if they grow, it will change the opacity of the dust grains locally. And what we get is that all these mid-infrared lines, these are the usual suspects we knew from Spitzer, all these lines would get boosted in their line strength as a function of time, simply because the dust grains keep growing larger, the opacity is going down, the gas to dust ratio is going up in the regions where these lines are emitting, and all of that makes them stronger. And then also, Arthur Bosman has shown that it makes a huge difference whether or not you include the shielding of UV photons by certain molecules in a consistent way, because also that can make, for example, in this case, this particular feature stronger or weaker. And so all of this has been studied, and I think we have fun now applying that actually to all of our models, and I'm coming to the end now, because I want to leave you with the 2 possibilities that we have. If we want to understand the diversity in the spectra, we have 2 options, and maybe both act together, we will see. Well, we can either do it through physics and radiative transfer, or we do it through transport processes. No? There are a lot of people who would say, well, it's all transport processes, depending on whether you have substructure or not, you migrate your stuff, your ices inwards, the moment. So it's all transport of icy material, either it works very efficiently or it's blocked by, say, the presence of substructure in the outer disk. And that can explain the diversity that we see, object by object. But there's another way to explain things, and this I took from your paper, Peter, because I really like it. I mean, in the end, when we look at the chemistry, it's pretty much an onion-like structure that we see, the most simple molecules on top. And as we need more and more steps in the chemistry to molecules, we go deeper and deeper into the disk. Now, as I said, it depends on how deep I'm looking into the disk. If my continuum is here, which means basically I have a cloud layer that I cannot look through, maybe I don't see C2H2, but I do see the other ones. So that is one possibility. And where that kind of continuum is that blocks our view can be different from source to source. Because maybe in the very low mass star disks, the dust grains have already grown, the opacity is lower, maybe I'm looking deeper into the disk. And that's why I'm seeing this whole reservoir of hydrocarbons, and C2H2 is just the tip of the iceberg. But as I said, we also have the possibility that that is not a smooth line to which I'm looking, because maybe there's substructure. If there are gaps opening because planets are forming, maybe there's less dust at a certain location. And so the depth to which I can look changes as a function of radius in the disk. We need to explore that. And then, of course, you could remove the material entirely. What if not only the dust has a gap, but the gas also has a gap? Maybe you lose the excitation conditions for a certain molecule, like HCN, for example, require certain temperatures to be excited. CO2 can be excited at lower temperatures. So maybe you would see CO2, but you don't see HCN. So this is still, you know, an open exploration, I would say. This is what we are embarking on now, to try to disentangle all these different phenomena. And with that, I would like to, first of all, thank the MINDS team. I think it has been a fantastic endeavor over the past year, more than a year now, to go through all this data, not only to reduce it in a very high quality way, but also to start to make sense of it. So it was a fantastic experience. It wouldn't have been possible with all these people helping with data reduction and analysis. And just to leave you with my take-home message, I think 2 points I want to make. One is we are still missing molecular data. So with the thermochemical models that we have, we can now also get back to the lab people. We say, we understand why we see these molecules with JWST, but we know from our chemical network, these other molecules are co-spatial. Please give us their spectra. Because we are very much limited in what the Hydra and Geyser databases give us at the moment. For example, molecular ions is something that we are only now embarking on to calculate the rotational constants, the spectroscopic data, so that we can do proper modeling. And the second point I want to make is this synergy between JWST and ALMA. For all our disks, we do have ALMA data, even though it's not like in a homogeneous survey. It's very heterogeneous with different resolutions taken. But to bring together the picture, how these disks look like on large scales and what we see on small scales, also allows us to understand the transport processes in the disks. We have disks that are very, very small in ALMA. One of the compact disks that Milou Temming is working on here, Tau. And still we see very rich spectra with JWST that, because of very efficient transport processes, we don't know. So we should look more into this. So with that, I would like to thank you.
Thank you very much. Any questions? See,
yeah, thanks for a very nice talk. So I have several questions. I'll ask one. So what's your opinion on slab models? Do they give us enough insight to the disk? Because for me, you can fit them with several temperatures and densities, things like that. But what's your opinion?
Yeah. So I think it's a very mixed bag, because we have lots of molecules where we try slab model fitting, and we see that the results are still very degenerate. So for many molecules, the only thing that we are quite confident about is the temperature, because that is very often not degenerate, because we see the width of the Q branch, for example, and that's very distinctive. In terms of column density, often we cannot constrain it much, so we have huge uncertainties there. And then, of course, once you're optically thin, you have the degeneracy between emitting area and column density. And so I would say, to me, it's a first step, understanding what we see, trying to make an inventory of at which temperatures do which molecule live. And then it's a first step in understanding it better. So, for example, the very first paper we published about a disk around a very low mass star was complete eye-opener because we saw this quasi-continuum. In Spitzer times, people thought they look at an edge-on disk and they see silicates and absorption. And it was Benoit Tabone with his lab models who could show that if we just make the column density ridiculously high, we get a quasi-continuum, and that explains perfectly the shape at 10 micron. And so they are incredibly fast and incredibly powerful in simply building up understanding. What it means, we need the 2D models to give them context and to be able to translate, what does it really mean in a disk context?
Maybe to iterate on this question, how is this looked at in the MINDS team? So you know that I was always very critical about these slab models. Mm-hmm. I never touch it. It's an option I import and never run. So I wonder, are the people happy when they have these output in form of column densities or temperatures, or do they feel like I do that we need actually to rather have that and then try to really make real models to explain those findings?
I would say again, it's a very mixed bag because we are still at a stage, I would say, where we are happy with the slab models in the context that it allows us to identify what we have in the spectrum. And I would say that in order to really understand an individual object with a full thermo-chemical model, it requires months of work. This is not something you can do very quickly. And so I think the slab model analysis, or whether it's Till's fitting tool, the little duckling, they are a very powerful way of analyzing the data in a kind of first step. And I think it's not taking anything away from the more detailed modeling, but I think it's a very first step that in any case we need to take, because we need to understand what is in the spectrum, even for setting up the correct thermochemical disk model. I think it is a required step.
Maybe other more general questions? Information.
Oh, I don't have a general question. I have a maybe naive question about the shampoo model.
Mm-hmm.
So you were saying that the reason the monomers don't pick up ice is they're preferentially in the bulk of the grain, but they're not on the surface. So is the model assuming compact spherical grains of some kind? No.
We can make it compact. So for the comparison with polymer, we actually force them to be compact because otherwise they take up ice's interior as well. So we got away with a kind of radiative transfer inspired picture of the grain. So we have a porosity. So you have all these monomers, but there's space in between. And so we said, what if our gas phase molecules basically go into the grain depending on how porous it is, and you get to a very similar e to the minus tau concept of how, as a function of depth in the aggregate, you actually are less and less able to pick up ices. And so we went for that, and we can change the porosity and we can understand the results. So the more porous we make it, the more we can take up.
But so when can you go back to the figure? The one where the Radimo has a higher ice mass fraction, right, than the shampoo at the ice line.
Yes, this one.
So in this one, you are assuming compact.
Yes.
Great.
Yeah, because otherwise we cannot compare to polymer at all. Yeah. Yeah, it's always a little bit a matter of what you want. So in the first paper, so this is the second paper we submitted, should say this first paper, 90% of that paper was just benchmarking against, each of the other papers, because there is a paper that deals with collisions, but it doesn't have like 100 AU disk. There's another paper with dynamics that only has vertical transport, one with radial transport. So we took all of those published papers, and one by one we descoped shampoo or switched off certain aspects and then reproduced their result, just to convince us that this is right, because as I can tell you from the debugging, it's so complex that there are many things that can go wrong. And even the referee of the paper in the end asked us or basically forced us to do a direct comparison to podium, absolutely direct. And that's why we went to compact grains, and we can show that absolutely as a function of radius, we get exactly the same ice fractions over 100,000 years. So we evolve Podimo 100,000 years further. We use shampoo to evolve 100,000 years further. We compare and we find the same result, which is kind of cool, but we were scared.
Can you show the other slide again? I mean, it's my understanding correct. So what happens here? I didn't understand that fully. Is that kind of in the core of these complicated grains, you have actually things that formed somehow further in or so? So it doesn't have the water, and then you have only on the surface a little bit of water? Or?
No, you have to see it like most of the time, a monomer sits inside a large aggregate, most of the time. If it sits very deep in an aggregate, the aggregate has a certain temperature, which is very close to sublimation temperature. And you can lose your ice, even if you're very deeply buried. But we only allow the monomer to take up ice if it's close to the surface. And because of all that collisional recycling, so at each radius here, the collisional recycling between monomers and the largest grains in your size distribution goes very fast. But still, most of the time you spend inside, deeply buried in an aggregate. And so you can easily lose ice, but you cannot easily take it up.
I wonder whether this is kind of already some kind of comet. So comets, when they get warm, they kind of efficiently get rid of the water, however deep it sits. Yeah? So in the end, if they come a few times close to the sun, the activity is gone, right?
Yeah.
But the other way is not so easy to include water even in the microstructure. That takes forever, right? And I think this might be this effect.
It is similar to it, only that now we do take the collisional recycling into account. None of these grains is old like a comet. You constantly remake these grains, and I think that is something we still need to digest and get our heads around, even as modelers of distance in general, like how much at any moment in time you recycle your grain size distribution. And what that means for the chemistry is something we're just starting to explore.
Any other questions?
For TW Hydra, I'm not sure if I understand correctly, but to reproduce these iron features, you need bound it in a rim, so that you have an extended region. And also needs to be at the right radius so that you have the right temperature. So do you think this makes then TW Hydra very unique and you will only find these features there, or do you also expect them?
Well, I think you have a little bit of leverage because typically I looked at CH3 plus, for example, and it also emits at 500, 600K. So I'm sure you could move the rim closer in. You could go to 1 AU and you would probably still see CH3 plus if it's a kind of rounded structure. But if you move it all the way in to temperatures of 1000K or so, at some point, maybe you don't see it anymore. You may not see it because it cannot exist there, or because your emitting area becomes too small. I mean, if I go back to that slide, you've seen how weak that CH3 plus feature is. Yeah, so this is like 10 millijansky. And this is at 2.4 AU, you have a huge emitting area from that rim. If you move that a factor 10 inside, your emitting area is a factor 100 smaller, and you will not see it. So it's also a matter of sensitivity then, whether you can see it or not.
So you also don't see them in other mines?
No, the only other target there are two other targets I know we have seen it. One is PDRs for all, that's Olivier Benet's paper from last year. It's an externally irradiated disk in a high mass star forming region in Orion. And the other one we have is XUA1, which is an object from the open time program of Magna Ramirez Stamos. And that's also externally irradiated, has a G0 of 10 to the 5. It sits in a very high mass star forming region. And also there, I think we see CH3.
Any other questions? Maybe the very last one, can you show the TW Hydra modeling attempts? And where you had the spectra, the full spectra. Yes. So I wonder you didn't dare trying to play with a C2O ratio. So I mean maybe TW Hydra has a carbon pure
Yeah.
rich inner disk.
The reason why we picked this one is because there was a previous paper by Arthur Bosman and Andrea Manzati who had already claimed that that inner disk has a factor 50 depletion in these two elements.
But in these two, in parallel, I wanted to ask about changing the relation between carbon, because when C2H2 is too strong in all your models, then why not reduce the carbon?
Exactly. So that would be my next step. Well, this paper had to come out.
I see.
This is the Mainz overview paper, and we have thrown in one object to give it a little bit of science context, but it had to come out, and that stopped my modeling efforts. And we said, well, what if we just confront these two scenarios?
I mean, just imagine that every of these models takes, I don't know, half a day to run,
but I have many more already on my disk, so that's not the problem. But I was forced to limit myself in this paper.
Okay, so let's take the speaker again. We will meet tonight, 6:30. If you want to join us in a restaurant, we're going to a Japanese place where you can have this noodle soup. I will send an email to everybody, so you are very welcome to join us. We are probably going with a number of people, but there's always room for improvement. If you have any questions, so Inga is here today and the whole day tomorrow. So if you have any issues, catch her up with her. You mostly find her in my office and maybe also visiting,
floating around.
Okay, thank you so much.
Yes, and I don't remember.
Yes.